Yeah. Okay, let's start our first lecture of matrix analysis class. I made some lecture note for you so we can have a better presentation of our contents from the textbook. Okay, yeah. Okay, matrix theory provides a theoretical and practical useful way of approaching many types of problems, as you see in here. It has a beautiful theories in it and has a wide range of applications in theory and in real world problems. Okay, we will start the textbook matrix analysis. You must see the syllabus here, and it shows all the details of our tentative plan for this semester. And I showed you the prerequisite for this course. So when you find any concept that you are not sure, then you can always go back to this information to review it, as well as other resources that are available for you. Okay, chapter 0, review and miscellaneous. Here it says vector space, blank inequalities, and inequalities, and the criteria for the non-singularity of a matrix, and Cauchy-Schwarz inequality, Gram-Schmidt also normalization process, orthogonal complement, which leads to the dual space of a vector space, and partitioned matrix, and include the submatrices and addition and multiplication of partitioned matrices, inverse of a partitioned matrix, and determinant, more determinant in details, including compound matrix and classical adjoint and inverse, and Cramer's rules, and several determinantal formulas. Yeah, it won't be difficult to find many formulas related to the determinant, such as Sylvester's identity and Cauchy-Binet formula. And there are a variety of special matrices: block diagonal matrices, triangular matrices, permutation matrices, circulant matrix, and Toeplitz matrices. And each of these Henkel matrices are an active research area of 21st century. Hessenberg matrices. Most of the analysts at our department working on this particular type of matrix, and Lagrange interpolation, etc. And change of basis that you have learned from the introductory linear algebra class. And eigenvalues, eigenvectors, including Lagrange multiplier and eigenvalue and eigenvector equations. And similarity and eigenvectors, not only right eigenvectors. You will see the left eigenvectors as well, and we find the relationship between left and right eigenvectors. and unitary equivalence and normal matrices, which we see in every articles that we read in these days. And canonical forms. There are many different canonical forms, such as the Smith normal forms and the Jordan canonical forms and many others. There are many of them. But recently, Jordan canonical form has been used more widely. But in early stage, other canonical forms were more popular. But these days, you're supposed to know about the Jordan canonical form, which has been used in the area of engineering. And Hermitian matrix and symmetric matrices. Real symmetric matrix is a Hermitian matrix, but complex symmetric matrix is not an Hermitian matrix. So this research on these two types of special matrices are distinct. Okay. And norms of vector and matrix. Here you will see the definition of matrix norm, not only a vector norm. And also we'll see the relationship between vector norm and matrix norm. Basically, matrix norm is induced from the given vector norm. You will see it for the first time in this class. And eigenvalue localization problems are covering Cauchy-Green theorems and overs of Cassini and many other variations of inclusion reasons. And positive definite matrices. The concept of positive definite matrix is a wide area of research. Quadratic form is a part of this chapter, and this is a more general chapter of all the things that you have seen before on special matrix. Positive definite matrix and positive semi-definite matrix give you the extreme of a function of many variables. Polar form and singular value decompositions are all comes from there, and you will see the applications of singular value decomposition as well. And non-negative matrix. On this chapter, you will see the Perron theorem and Perron-Frobenius theorem for the non-negative matrices, and also primitive matrix and general limit theorems and stochastic and doubly stochastic matrices. And this primitive matrix has many interesting graphical and combinatorial properties. In order to cover those, we need some concept on convex function and convex set and fundamental theorem of algebra and some background of analysis class. Okay. And this is a recent work classification on research areas of matrix analysis. Part 1 is on linear algebra, and Part 2 is about combinatorial matrix theory, and Part 3 is about numerical linear algebra, and Part 4 is on applications of linear algebra, and Part 5 is about the softwares. for the basic linear algebra, yeah, you should know all those things, and after you finish this class, you shouldn't have any problem with this basic linear algebra. The next step is advanced linear algebra, such as function of matrices and multilinear algebra that leads to tensors, and matrix perturbation theory, and matrix equalities and inequalities, and singular value, and inequalities on singular values, and numerical ranges, and matrix stability. And the next is about topics in advanced linear algebra. This is the active research area of these days. Inverse eigenvalue problem is one of the hot area, and linear preserver problem has been published more than 600 papers in the last 10-20 years. And matrix leaving a Kohn invariant, and all these are related to the invariant theory. And the next part is about combinatorial matrix theory. Professor Richard Broaldi wrote on about 20 pages of survey on combinatorial matrix theory, and the permanent is a part of it too, and sign pattern matrix and matrix completion problems, and those are the things that we have worked at Seongyungan University. And the part 3 is about numerical linear algebra. Here we use vector and matrix neurons and least square solutions, and numerical methods for the eigenvalues, such as computation of singularity compositions, and these are the things that is growing fast. The impact factor of numerical linear algebra, it was all new in 10-15 years ago. The journal on numerical linear algebra just published in last 10-15 years ago. It was just a baby, but now it is more wide, and the impact factor of that area is about twice and triple of theoretical linear algebra these days. So, yeah, you should be aware of the changes. And computational linear algebra, such as matrix computation and large-scale matrix computations. And also this application is growing fast because the theory has been developed very rapidly over the last 50-60 years. And also, the computational tools and skills has been, and algorithms has been developed very wide range. All those makes lots of changes on solving real problems, which was not able to be treated with the traditional tools. The applications are on many areas. Yeah. Statistical analysis, Markov chains, and differential equation and stability, and dynamical system and linear algebra, and control theory. And those are the courses that we can offer from our graduate courses. And linear algebra and mathematical physics, and linear algebra and biomolecular modeling. And this is also quite booming areas. And coding theory has been a traditional applicable area of linear algebra. And signal processing, and geometry, the use of linear algebra in geometry, and matrix groups, and group representation. This is applications to abstract algebra. And real algebras are all related to what You have learned and you will learn. For the computational softwares, and MATLAB, and Maple, and Mathematica are three big tools. And RAFX and BLAS, and all those are the things which made all those commercial softwares are possible. But these days, more on web-based tools such as Java's and Sage are all having a leading edges. So for example, Sage Math are using not only Java tools, but it also uses Mathematica command and Maple command and MATLAB command as well. So in 5-10 years, you will see most of the computational things can be done on the web. Okay, also there are many softwares for linear algebra which are free. Okay, those are the things that you should know about. We should have a big picture of the working area of our research and find out what will be our area. But also we should be aware of other areas as well. Yeah. Now we start with preliminaries. Algebra. An associative algebra is a vector space over a field F with two operations. One, multiplication, associative algebra is a vector space of A over a field together with an operation xy satisfying two distributive properties and associativity. These rules. So associative algebra is a vector space. Usually when you say algebra in this course, it means associative algebra. One of my introductory linear algebra class student asked about algebra. What is the algebra? Last evening, and it has a wide. So I try to give the answer, and from the very introductive to the advanced. Nowadays, the Wikipedia has been good tools for it. The English version of it is pretty well established now, but Korean version of it barely started, so we can add our corrections on it. It has a function to edit it by ourselves. So even the freshman students are also interested about algebra, not only linear algebra, but associative algebra is itself a vector space. That's what you're supposed to know. The vector space of n by n matrix over a field F, particularly with the matrix of multiplication, is a well-known algebra. Boundaries. The boundary sigma S of a set S. The boundary of a subset S of a real number or complex number is the intersection of a closure of S and the closure of the complement of S. For example, the boundary of the subset S is of this set is itself a circle. Boundary, the closure of the set and the closure of the complement. So it gives us the circle. Next, convexity. when V be a real or complex vector space, then subset of V, these are the subset of V, then vectors of the linear combination of those vectors is called a convex combination of this. Here, this coefficient, the summation of these AIs should be 1. Here, the summation note has been missed, but you know it. So, linear combination of the given vectors with the summation of those all coefficients is equal to 1, then it is called a convex combination of those set of vectors. A set is called convex if any convex combination of vectors in S is in S. So convex combination of any vectors is in the set itself, then the set is called the convex set. Convex hull of S is a set of all convex combination of S, and it is denoted by con of S. The extreme point of a closed convex set is a point in S that is not a non-trivial convex combination of other points in S. So for example, this is a typical convex. This is a typical polyhedra, and this is a typical example of a convex set. Then this point, which is called the extreme, this end point. These are called the convex, extreme point of the convex set. This point can be written in this way. If this is a vector and A's are between 0 to 1, then this should be a same point. So that's the mathematical presentation of this extreme point of a convex set. And convex polytope is a convex hull of finite set of vectors. For example, if we have 3 points here and here and here, then this triangle is a former convex polyhedra, convex polytope. Okay? It's a convex hull, and also it is a convex polytope. And a function on a convex set is called convex function if for A's in between 0 and 1, for those A's, if we satisfy this inequality, we call the function is a convex function. Okay. From these definitions, we can prove several things, such as Klein-Milman theorem, which you can find at Horn and Jones's textbook. The compact convex set is a convex hull of its extreme point. This is in the appendix of this. Okay. So these are the examples of convex combination and convex set. And elementary symmetric function. This is what you should know. You might have seen it before, but you should know now. The case elementary symmetric function of alpha I is defined in this way. From alpha 1 to alpha n, choose k in order, and find the product of those k element and add those. So how many terms that you have here? How many terms do you have, Mr. Jin? There are n terms. We choose k. And choose k. We have n choose k terms to be added. Just choose k element out of n, then give an order on it, and multiply those in that order. Okay, next. So for example, S2 of alpha 1, alpha 2, alpha 3. In that case, choose 3 out of these 3. So 1, 2, 1, 3, and 2, 3. Those are 3. That's all. So 1, 2, and 1, 3, and 2, 3 are all. Just add all those. Choose S1 of those n terms. Then choose 1 terms from n. So that will be the all n. So just add all those n terms from A1 to AN. So, and next, the last example is Sn of those n terms. That's the choose n out of n. That's only 1 term. Every element is there. So just productive, and that's it. And greatest integer function. Sometimes it's called the ceiling function. Yeah, you know it very well because this is a part of scholastic aptitude test, SAT exam for the college entrance examination. So every Korean student knows about the ceiling or a floor function. That official name of it is a greatest integer functions. And multiset. Multiset is an unordered list of elements that allow repetition. So any set is a multiset. But some multiset like this is not a set. For the definition of a set cannot have a repetition of one element in a set. Multiset. So we will use it. Group, yeah, you know well about groups. Group is a non-empty set with a function here with associativity and additive identity and additive inverse. And also it should be closed on this function. This writing implies the closedness of the operation. So the group is abelian if it is that the operation is commutative. So any vector space is abelian under addition. Set of invertible n by n real matrices is a group under the matrix multiplication, and set of all permutation of a set is a group under composition. And we next define field, because ring is defined, and the examples of ring is defined from a field. So we start field first here. Field is a set F with at least 2 elements together with a function called addition and multiplication. Satisfy the following actions: commutativity on addition and multiplication, associativity for these, for the addition and the multiplication, and additive identity, the existence of it, and the existence of an additive and multiplicative inverse, and the existence of additive and multiplicative identities, and distributive that mix those operations. The most important example of the field is a real numbers, set of real numbers, and set of complex numbers and rational numbers. These are all field. But the set of integers is not a field. Ring. Ring is a set together with a function. You know these. One addition and the multiplication that hold the commutativity on the addition, associativity on both addition and multiplication, the existence of the additive identity and the existence of additive inverse, not for the multiplications. And distributive rules of these two. This is the definition of the ring. And zero divisor in a ring is a non-zero element A such that there exists a non-zero B, that AB is equal to 0 or BA is equal to 0. So, the set of integers is a good example of a ring. And any field is a ring as well. To be a field, then this set, n by n, set of n by n matrices with matrix addition and matrix multiplication. Okay. Then this is a ring. This form a ring. This set form a ring. Also, that shows what is the zero divisor in the ring of n by n matrices. Okay, and big O and little O notations. A function f is called big O of G if there exists constants C and K such that the absolute value of f of x is less than or equal to C times absolute value of g of x for all x which is bigger than or equal to k. So if you have this C compared to this function, then we call the function f is big O of g. And the function f is called little o of g if the limit when x goes to infinity, that f the value of f of n over f of x, f of x and g of x is equal to 0, then we call it's a little o of g. Okay, this will be needed to compare the functions. Also, that will be used for the matrix norm, so deal with the inequalities of those vectors, norms, and functions. For example, this function is a big O of x square, and ln of x is a function of little o of x. Okay, now we start the chapter 0, review. Introduction and vector spaces. What's the vector and what's the operation of the vector addition and the scalar multiplication, and what is a scalar field, and what is the vector spaces. I typed all this by myself, and subspace and spans and all these things, but I found out this year this matrix analysis course should be taught in English because we have a foreign student here, so I had to go back to the English textbook. So I will use the English versions there. But I spent pretty much of time to make a lecture note to make you understand better and easier. Here, it says the definitions of vector space and things. What is the definition of vector space? Mr. Jung, what's the definition of a vector space? What you can say? Hana, what you can say? What's the definition of the vector space? A set of vectors, or a set of object, which is called a vector, form a vector space if it has two functions, one vector addition and one scalar multiplication that satisfies how many conditions? How many conditions? 8, 10 conditions. Yeah, 2 basic conditions and 8 operational conditions. Okay? Yeah, those are all written in there. This is another way of writing. 10 conditions, 5 conditions, and 2 conditions, and 3 distributed laws. This is another way of remember. And subspace and spans, yeah, you all know this, so I will not go through it. Basis and extension to a basis. Suppose we have a linear independent set in a vector space V, then we can always find a basis that contains those linear independent subset. Okay, so it's called a basis extension. You should know it. And dimensions. Homomorphism and one-to-one and onto, that says one-to-one correspondence. It makes us isomorphism. So any n-dimensional vector space over F is isomorphic to Fn. That you know it. And linear independence, dependence and independence, and extensions and dimension isomorphism, and matrix. Yeah, you should know the definition of matrix. And linear transformations, properties of linear transformations. And also, yeah, from here, there are vector spaces associated with a given matrix or linear transformation. From here, we can, some of those are domains and null spaces and ranges, and those holds this type of the relationship, which is called the length nullity theorem for the matrix and length nullity theorem for the linear transformation. You should know about this length nullity theorem in detail with the full detail of the proof. And matrix operations and transpose and Hermitian adjoint and all these. And meta mechanics of matrix multiplication and determinant and Laplace expansion things. So I have made some abstract of those. Matrix is an n by n area of scalars from a field F. So it's just area of scalars without bracket. There's no definition of, no use of bracket in the definition. Okay? That you should know. Definition of linear transformation. And range and null space and length nullity theorem, you should know the proof. And length nullity theorem. Here, this is a meta mechanics of matrix multiplication. Yeah, suppose we have a matrix like this, then J's column of AB can be written in this way. And also, this is the product of this matrix and the columns of this matrix. The Is law of matrix AB can be written as a Is law of matrix A times the matrix B. And also, that can be extended in this way. Ij's component, Ij's entry of ABC, the product of three matrices, can be written as Is law of A times matrix B times J's column of C. And also, this matrix times vector X can be written a linear combination of the columns of the matrix A. All these will be used in chapter 1 to prove things. Okay. Similarly, yeah, we can think about right and left product of the vectors. This will lead to the left eigenvectors and singular value decompositions. Okay, and alternating sum that give us the definition of determinant. But original definition of the determinant is is from the other way, but this is also equivalent definition for the determinant as well. Here, we did use this the group character sigma as a sign function. If we change this function to other characters of a group by using the group representation theory, then we will have a variety of other matrix functions, not only a determinant. It can be permanent, and it can be defined on the subgroups of the matrix, not all symmetric groups. And also, we can have many other group characters that can be used to define generalized matrix function. My master's degree research started on this generalized matrix function. Actually, Professor Leroy Beasley is the one who proved the permanent function is not multiplicative. So that was the one of the papers that I had read when I was a master's student. So generalized matrix function was an interesting area, but it also leads to the tensor from here. Tensor, the theory on tensor starts from this generalized matrix function. And also multilinear algebra started from here. Elementary row operation, you know it. The type 1, type 2, type 3. What this book said here is what type of matrix that you multiply, on which side to make those elementary row operations. That leads to the low reduced echelon form, low echelon form and low reduced echelon form, and Gaussian eliminations. These are all from those basic operations. And the multiplicative property of determinant. How you prove this fact? Holodakpa, how do you prove this equality? Block matrix. In more detail, I want more detail of the sketch of the proof. Mr. Jin, how do you prove? How do you prove? Hana? Low echelon form? First, we show this is true for any elementary matrix, like this. This is true for the multiplicative properties working for elementary matrix first. We show it. There are 3 types of elementary matrix. For each type, that works. You show it first. Then, you show it for the, like Hana said, then we can use that fact to have this one. So take Gaussian elimination here. So we have the elementary matrix EK2, E1, and B here, like this. Since we showed this multiplicative property works for the elementary matrix, we expand it to the general form of it. Then we have this multiplicative works on every matrices. In that process, we divide it as 2 cases, one for the non-singular case, one for the singular case. That's the standard procedure. If you choose it this way, that you can show it easily. But if you just try it directly to prove it, you're going to spend lots of time. So you should know the standard technique to attack the real problems. and functional characterization of determinant. Here, this is the definition of the determinant that you have learned from matrix theory class. Okay. Matrix, the determinant is a matrix function defined on the set of matrices to the scalar field, real number or complex numbers, depending on the scalar field that you are using, satisfying these three conditions: multilinear on each columns, and alternating function, and also is normalized. The image of the identity matrix is equal to 1. There are only one unique functions that satisfies these three conditions, which can be written in the other way that you saw as an alternating matrix functions, which is now widely used as a definition of determinant. Rank definitions, rank and system. Here, so here determinant, I show you the Laplace expansions here and alternating sums here as a definition of determinant, elementary row operations. And this is the functional analysis of the determinant, of the definition of the determinant. Determinant is a function on matrix function satisfying these three conditions, and all reduced echelon form and etc. And with those, now we can see lots of things. Now we have many definitions. With those definitions, we can find the properties of it. For example, rank. Rank inequalities. Rank of A, whose size is m by n, cannot exceed m or n. You know it, because the maximum number of linear independent rows or columns are not more than m or n. And this or this. The rank of addition of two matrices is less than or equal to the rank of the addition of the rank of each matrix. And you should be able to prove it, and you know it. These are the things that you should be done when you should know when you are a sophomore student at the college. And these are the things that you now have to check. Rank of A star is same as rank of A. Hannah, how do you show the rank of A star is same as rank of A? How can you show that? This is a well-known fact, very well-known fact. But proof of this is not easy. This is a very well-known fact, and everybody knows it. But in order to prove this rigorously, you should understand the Jordan canonical form of the given matrix very well. Without it, you cannot prove it easily. Okay. Is there any volunteer to prove this? Any volunteer to prove it? Hannah, wanna try? Okay. Yeah, that's your problem now. Okay. And also, this is one of the things that you see in the midterm or final exam of linear algebra class. And also there are many things. There are ranks and rank inequalities here. Here, I made a homework for Hannah. So, including that, try to show this. And I also give some problem to work for Mr. Jung, Ji-hwan. Yeah, you try to show this. I gave some sketch of the proof already here for Jung, and also I explained it in detail when you had the mathematical modeling class last semester. So you should finish the proof by yourself with these informations. And this. Okay? Mr. Zhang? And also non-singularity. This is the sum of the if and only if condition for the non-singularity of the matrix. Inner product. Here, actually, I typed all this. Proof of 17 equivalent conditions. This is the one choice that I made. This is a draft of it. Some of my students typed it as I collected. But so this is all. If you go in, this is long proof. But if you know this, that means you know. And it's 5 chapters of the linear algebra books. This one theorem can evaluate you or knowledge on the linear algebra class of the half of the linear algebra textbook. But now, since you have seen some of these problems in your midterm and quizzes, this is all together. Yeah. Okay. And Cauchy-Schwarz inequality, I will not ask it anymore to you because I believe every one of you knows about the Cauchy-Schwarz inequality and projections. If you don't know it, then you are not a graduate student. You are not even a math students here. And Gram-Schmidt normalization process. Yeah, you should know it. This Gram-Schmidt normalization is the main goal of the freshman introductory linear algebra class. If you want to pass linear algebra class, you should know this. That's it. So actually, I gave some more of this in detail. And also, if you know the Gram-Schmidt normalization process, you know QR factorization. QR factorization just directly from Gram-Schmidt normalization. But in here, I have dealt only on the square matrix. Also, on square matrix case, Gram-Schmidt normalization process, the understanding of it is enough to finish all the theory. But for the rectangular case, you need more knowledge to do it. Yeah. In this matrix analysis book, we cover this. So also when I ask you, you know it. Yeah. If Harold Akbar, you should know about Gram-Schmidt normalization process. Gram-Schmidt. Yeah. If you don't know, then you have to go through it. You have a linear algebra textbook. Okay. Not only this book, the easier one, introductory course. Yeah, there are many books in our lab, so you can choose. Since you taught some linear algebra class in your country. You did. So I don't worry about it. Okay. Okay, yeah, the QR factorization. Yeah, QR factorization is directly from it. Yeah, this is one section of the introductory linear algebra class. Okay, the next is partitions matrices. Here, I give some notation to understand the submatrix and partitioned matrix. So here, QRM. This notation is very important when you go through this textbook. QRM. This is a set of the subset. How the subset is consists of? It is from this set of M elements, you choose R and arrange it in the order, lexicographic order. Then you have how many elements did you have here? You have a set of M choose N subset. You have a subset of that number. Okay? So, for example, A is here, so alpha is here and beta is here. So let A is n by n matrix, and alpha is the length of alpha is R, and the length of beta is S. Then you have alpha and beta here. Then this is a submatrix of A with alpha rows and beta columns. But these alpha rows and beta columns alpha is a subset. So it's R element out of 1 to M. So you can have 1, 2, 3 to R, or 1, 3, 4, 5 to R plus 1. So this alpha means of the columns, the rows of the R rows that you choose from M rows, and this beta give you the R the S columns from N columns. So this is submatrix of R by S, of size R by S. Submatrix of A of size R by S. This alpha and beta. This is submatrix of N minus R and N minus S. So when I use this, this means including. When I use this, this means excluding. Understand? Okay. So if I choose one with a closed bracket and one with the open bracket, that means this we have R by how many? N by S submatrix. Okay? Like this. So this is a notation. Particularly, Harold Akbar, you should know this, because your homework, you should use this notation. Without this notation, it's very hard to prove. Here, so I give you. So there are some formulas for the partition matrix. If you have a partition, if you have a submatrices, then some formulas for the determinant can be written with those submatrices. Next, the determinant again. The more topics on determinant. The first is about compound matrix. The compound matrix are using this notation. You see, Mr. Jin? Yes, alpha from here and beta from here with a K element out of it. Then, suppose we have a 3 by 3 matrix like this. Then think about C2 of A. This is a compound matrix. Second compound matrix of 3 by 3 matrix A. Then this matrix consists of 2 by 2 matrices and determinant of these. So from alpha here, so we have, for example, if we like this, then we have the first element of this compound matrix is it's lexicographic order. So 1, 2, 1, 3, and 2, 3 here, and 1, 2, 1, 3, and here, and the others are here. We have the 1, 2, and here 1, 3, and 2, 3 like this. Okay, so that gives you all this. So you have the second compound matrix of 3 by 3 matrix A is defined in this way from the given 3 by 3 matrix A, which is this. So from a matrix, you developed another matrix from there by using the determinant. And this matrix has a very interesting properties like this. Something like the determinantal properties like this. And many other interesting facts. So from now on, if you have a matrix, then you can deal with it. You can create another matrix. And also you can do research on those matrices by yourself. Okay? Those notations are used here to find the classical adjoint and inverses like this. Adjoint is defined in this way, and you know the depth here, you know this theory. Mr. Zhang, do you know this identity? How do you prove it? How do you prove it? All you have to use is Laplace cofactor expansion. That's all you need. If you know the Laplace cofactor expansion, it's done. Actually, from the textbook, you can from the elementary linear algebra textbook, there is a full proof of this. Check it. Okay. And for the compound matrix, so the definition of compound, I gave you more detail of compound matrix like I gave you. And this has this many properties. This, particularly this one, this and this are important. These two are very important. And also, like prelim exam of any of the major university, like University of California, Berkeley, or MIT, or any other places, if you have a prelim examination, these are the problems that you are facing. Not only abstract algebra. Most of the prelim exam on algebra, more than 30% of the problems are from linear algebra, matrix theory like this. So if you want to be qualified as an international standard, then you should know all this. So those students who do not take the course on this, actually not well qualified for the standard that every other schools are pushing. Okay, this identity, this equality, is called the Sylvester-Planck theorem. You can find the proof of this theorem from this article which was published in 1952. If you just click it, you will find it. And Cramer's rules and minors and things like that. Here, this is what I mentioned to you. So there's nothing wrong with it because from the definition that you saw on matrix, there's no bracket. But if without bracket, it's easy to make a mistake. So you just give a bracket to see, to classify. Here, all you have to do is just the Laplace cofactor expansions. If you know it, then you can find the formula for the inverse like this. And Cramer's rules are just using this here. So these are all the things that you already know. And since this is a common exam problem, so the elementary linear algebra class, you should know it. Sylvester's identity and Cauchy-Binet formula is the things that you are seeing it now first. But this is also using the notations that we have defined, which I showed you before. And see this. This is about the multiplicative property of the matrix. Okay? Multiplicative property. But it's more general. Not only for the n by n matrix. This Cauchy-Binet theorem is about the multiplicative of submatrix. Yeah. So Cauchy-Binet theorem. If you go this website, Planet Math, you will see the full detail of this Cauchy-Binet formula. And this is a special case. This matrix multiplicative property is a very special case of this Cauchy-Binet theorem. Yeah. This is a homo. Proof of this is a homo for Holodagba. And actually there are proof here, so you should be prepared to introduce it. Okay? And the others are special type of matrices, such as this. Diagonal matrix, block diagonal matrix, triangular matrix, permutation matrix, circular matrix. And each of these has a very interesting features. And each of these are working areas. If you go one special matrix, there are a variety of areas that you can do your research with the tools that you've learned from other sections, other chapters. You don't have to go all those, but if you have an interesting particular special type of matrix, then you can really attack on it with the knowledge that you've learned from other chapters. The next thing is the matrix and Lagrange interpolation. For the Lagrange interpolation, you should know about the van der Monde determinant, van der Monde matrix. Suppose you have this matrix, the determinant exists. Suppose you have this matrix, then this is a determinant. This is a van der Monde matrix and this determinant. The proof is given like this, and most of the students, undergraduate students, knows about it. And this is about the Lagrange interpolation. This is a algorithm to do it, and this is a theory, curve fittings. And all these are in our elementary linear textbooks. And this is a tool. This is a tools that you can this van der Monde matrix and its determinant can be used for the Lagrange interpolation. Lagrange interpolation, which gives you the least square or just curve fitting passing. It takes time. Yeah. So browser. Okay. Now this is the software that I developed with Java virtual machine should be. I will show. You can do it. Yeah. You can do it. You can try. Yeah. I can do it easily. Okay. Anyway, here if you have 2 points, then you can find the line. If you have 3 points, you can have a further education, and you have polynomials. This software that I developed with Richard Wellman at Westminster College at Salt Lake City, and it holds all those algorithms with research schedule. Okay, and there are something. And next thing is a change of basis. You should know about this, but some of you may forgot some of the details of it. So you should realize this. So I will try to give you a quiz on this change of basis. This change of basis is all about this. Chapter 8.1 of Contemporary Linear Algebra textbook 9. Matrix representation of linear transformation. If you go here, then you will see. Oh, here. Do you see? Do you see here? See, this is a line that passes to this point. Polynomial degree of 2 quadratic lines. This is a polynomial. Suddenly it calculates all the things in there with the algorithm that I showed you. This is a Lagrange interpolation. But these are the things. This doesn't pass through it, but this is the least square polynomial that has the least errors that passing through it. Isn't it interesting? Okay, yeah, those are the things. But for this change of base, you just go through it. Since you'll find it easy to catch it. Just find how to find for the given linear transformation, how to find the matrix representation of it. You just multiply on both sides, then you will see. With this matrix, then you have what? You have a change of basis. How to find this? This chapter deals with the change of basis. T is the same one function, but if you choose the different basis, the shape of that matrix representation are different changes. That's the change of basis. This is the matrix representation of the linear transformation. Okay, so yeah, just go through it. Yeah, I will. I will just test. I will give a couple of problems from only this section, these exercises, not others. Just go through the exercises of this elementary text. Only on this. Okay? And also that's on the web. Here, if you are not sure, then contemporary linear algebra, here, chapter 8, go 1 here, then there is everything in here. And also you can listen the lecture that I have saved. Okay, so I will to review all the things. Okay? So in next hours, so try to put your solutions and things on the iCampus, so make a discussion with it and complete.
자, 행렬의 대각화 8장. 행렬을 대각화하는 것은 수학적인 중요성 이상으로 이 응용이 굉장히 다양해요. 굉장히 다양해요.
So you can always go back. And also, so in order to help you to do your homework, I typed all this for the notations and some basic informations. So, and the problems typed here, and the proofs are typed here. Some sketch of it, all here for Mr. Chung and Mr. Jin and Miss Kim and Mr. Hololdakvas are all here. This file and with this, so each one of you has one problem, and all of you so work together to just go through the proof here and make it more complete. This theorems, and at last, change of basis. You just go back here and go through it. There's a problems there and just check it. That's it. So this file is on iCampus here on Q&A. So you just download it and just do your part. Here, this is the file that I showed. So you have everything now for the preview and review of the chapter. Next time, we will go from there. After we finish it, then we'll start chapter 1. Okay. Any questions? Any questions? Okay, then let's clear.